Okay, so we're going to tackle two problems here. The first problem is going to be a box that is being pulled along a rough surface of coefficient of friction, kinetic coefficient of friction of 0.2. We're going to pull it for 10 meters, and we want to know how fast it's moving at the end of that 10 meters. And we can work with kinematics if you want to. If we can work with forces, which is going to lead back to kinematics. But we're actually going to talk about energy. All right, so we're in the subject of energy, and up here we've got our different equations for energy that we're going to work with, all mechanical energy. Energy due to gravity, potential energy due to gravity, kinetic energy, the energy of motion, potential energy due to spring, and we have work. And so the first thing that we would need to look at is there going to be a change in height? Because if there is, then we probably need to consider the first potential energy. If there's not a change in height, then we don't need to worry about it. So if we look at this, it's a flat surface, and we don't need to worry about a change in height. So that's out. Secondly, do we need to worry about a spring? Nope, don't need to worry about a spring. So in this problem, really, we're just working with kinetic energy and work. Kind of ironic. So let's look at everything here. What's going to make this thing move faster? And the answer is probably going to be, well, that 100 Newton force is probably going to make it move faster, right? But is all of the 100 Newton force going to make it move faster? Well, no. Part of it is actually going to be pulling up on this box, and the other part is going to be pulling it to the right. So we have these two components that we need to consider for this 100 Newton force. Okay? And so that's a 30-degree angle, so I know that this side should be 50, hopefully, and that this side should be 86.6 newtons. All right, and that's just doing 100 sine of 30 and 100 cosine of 30. So if I look at this, we've got this 86.6 Newton force pulling to the right. As it's pulling to the right, is there a force that's pulling to the left, trying to slow it down? And the answer is, well, we have friction, right? So if we drew a free body diagram of this thing sliding across to the right, what we would see is that we have the force of gravity, and that's 150, 15 times 10, and we have this normal force pointing up, which is not 150 because of that, okay? We have this force pulling up and to the right, that's 100 newtons, and we're going to have some force of friction. Okay, this is just going back to forces now. And so if we did the sum of all forces in the y direction, we'd see that we have normal force going up, we've got 50 going up, that component of 100, and we've got 150 going down. And there's no acceleration in the y direction, hopefully. And if that's the case, in order for this to equal 0, then we have 50 minus 150. Fn would have to be 100. Okay? 100 plus 150, or 100 plus 50 is going to be 150. That's going to cancel each other out very nicely there. So, once again, make sure your normal force is not going to be equal to the 150 force of gravity. We're pulling up on it a little bit. All right. So the other thing we need to look at is the x direction, the sum of all forces in the x direction. And the forces in the x direction, we've got 86.6 pulling to the right, and we've got a force of friction pulling to the left. Well, force of friction is normal force times mu. And we have normal force, that's 100. Mu is 0.2. Okay? So what's 100 times 0.2? Well, that's going to move the decimal over two places. And so we've got 20. So 86.6 minus 20 is 66.6. Ooh. And that's how many newtons we have in the horizontal. That's the net horizontal force. So let's look at this now. So what forces, what kind of energy do we have in the beginning, and what might cause it to have more energy later on? Well, the energy in the beginning, we have none. Now, if you said potential, if you thought potential, we actually don't have potential here. We don't have a pent-up spring. We don't have this thing up at a certain height where it can fall down. So we actually don't have any energy to worry about. Now, as it moves over to the right, do we have a net force that's acting upon it? Well, we do in the x direction. 66.6 newtons is acting in the x direction. That's our net force. That's our leftover force. It's going to cause some acceleration because force is equal to ma. Okay, so we do need to worry about that. But let's think about this in terms of energy. Once again, in the beginning, we have no energy. At the end, we probably have some kinetic energy, right? Well, what's going on with that? If we have conservation of energy, shouldn't that say that energy in the beginning is equal to energy in the end? And it should be true, but what are we doing to it? We are actually providing energy to it. We are giving it energy. So we're using some of our own energy. We're providing the force. We are actually giving this thing energy. So in the end, our energy is going to be kinetic energy. That's 1/2 mv squared. And so the question is, what's giving it this kinetic energy in the end? Okay? And so something has to be giving it kinetic energy, and we should know from earlier videos that work is equal to a change in kinetic energy. Okay? And work is equal to a force that is parallel to a certain displacement. And it just so happens that we have a displacement, it's 10 meters, and we have two forces that are parallel to that. We've got the 86.6 Newton force that's going to the right, and we've got this force of friction that's going to the left. Now they're fighting each other, and this 86.6 Newton force won, and it won by that much. So overall, we have a force of 66.6 newtons acting as the force over this distance that's going to give it kinetic energy, and here's how we write it. The work done is equal to the change in kinetic energy, right? The work done is a force applied for a certain distance. Kinetic energy is 1/2 mv squared. Okay? Because the change that we're going to have, it goes from 0 to something, and so the change is just 1/2 mv squared, whatever we get. The force that we have here is twofold. We have 86.6 newtons trying to make it go faster. We've got 20 newtons trying to make it go slower. And we already knew that was 66.6. I'm just writing it out. Both of these forces act for 10 meters. And that's going to equal 1/2 the mass, 15, times the velocity squared. Okay? So what we should gather from this is that the 86.6 Newton force is actually making it, it's actually giving it positive energy. It's doing positive work. It's positive. Friction is doing negative work here. Now, will friction always do negative work? No. No, friction often does positive work to make things go faster. That's actually how you move faster whenever you walk. Okay? But in this case, friction's taking away energy, and the net force, the 66.6 newtons, is really all we care about. So we have 66.6 newtons acting for 10 meters, and that's going to give us a change of energy of 1/2 mv squared. Okay? And now this makes it pretty easy. So we have 66.6, and we have that multiplied by 10, so now it's 666. We're going to multiply by 2, and we're going to divide by 15, and then I'm going to square root that. And our final velocity is equal to 9.42 meters per second. Okay? And that should be okay. Now, if we really wanted to work it out, we would say, okay, let's work it out the original way. What's the acceleration? We'll take 66.6 divided by the mass. That's 15. So our acceleration is 4.44 meters per second squared. And then, we'll run that through an equation, maybe the equation that doesn't rely on time. And so final velocity squared is equal to initial velocity squared plus 2 times the acceleration change of x. The initial velocity is nothing. We have 2. Our acceleration is 4.44. We have a change of x of 10. We're going to square root that to find v. And so we have the square root of 2 times 4.44 times 10. And I get 9.423, or same number that we got before. So it's the same thing. That's that second equation. We keep on running back to that. That is the energy equation. But you really need to know how to use 1D motion to use that. So that's this problem. We're going to move on to another problem. This is the roller coaster problem. And here's my little roller coaster that I have. And we're going to say this is a frictionless roller coaster. And we're just going to say that it has a mass of m. And it starts off at the top of a 50-meter hill. So it's been pulled up by a chain. This motor has done work on it, and now it's all the way up here. And so this roller coaster is going to go down, no friction, and it's going to get faster. It's going to go up here, get slower, and it's going to go down here and get faster again. And so let's talk about this in terms of energy. Well, what kind of energy does it have at the beginning? Well, it kind of really matters if it's moving or not. So let's say that it is moving, and let's say it's moving at a rate of maybe 2 meters per second. So it's really not moving that fast. Well, let's take a look. We have 2 meters per second there. How fast should it be moving here? How fast should it be moving at the bottom? Do you think it's going to be moving at half the speed that it would be down here? Is it that kind of change? Is it linear like that? Well, this is where we're going to find out. So we have 3 points, actually. Well, actually, 1, 2, 3, 4 points to talk about. A, B, C, and D. Now, if we have no friction whatsoever, the energy at A, the energy at B, the energy at C, and the energy at D, all 4 of those energies should be equal to each other. We need to account for all of it. So let's write that. The energy at A should be equal to the energy at B, is equal to the energy at C, is equal to the energy at D, and so let's talk about the types of energy that it might have. In the beginning, is it moving? Yep. So we've got kinetic energy. In the beginning, is it high, and could it potentially get lower? Yeah, it's got potential energy due to gravity. All right, no springs, right? At B, is it moving? Probably. So it's got kinetic energy. Can it potentially get lower than it is right now? Yeah. So it's got potential energy too. Okay. Point C, is it moving? Yeah, most likely. Kinetic energy. Can it get lower? Yeah. Potential energy. Point D, is it moving? Yeah. Probably moving the fastest it can be, right? It's at the very lowest. Can it get any lower than that? No. So while we could write potential energy there, the H would be 0. So for this, let's go ahead and replace this equation. For energy of A, we've had 2 types. 1/2 mv squared at A and mgh at A. At B, we have 2 types. 1/2 mv squared at B and mgh at B. At point C, we have the exact same thing. 1/2 mv squared at C plus mgh at C. And lastly, we have point D, where our energy is just kinetic. We've lost all of our potential. And there we go. All right. So if you notice, don't get confused by equals, 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 equals. It's like saying 5 is equal to 2 plus 3 is equal to 6 minus 1 is equal to, 9 minus 4. It's all the same thing. All right. We're just setting all these things equal to each other. So every single thing has m, which is good. So we cancel it out. And if we wanted to, we could find out how fast it's moving at any point. So let's pick a random point. Let's pick C. All right. So at point C, how fast is it moving? Well, we have information about A, and we're talking about C. And so let's go down here. We have 1/2 mv squared mgh for A, and we have 1/2 mv squared and mgh for C. And that's all we need to concern ourselves with, so let's do that. And remember, all these m's are gone. Let's just go ahead and cancel them out. So we have 1/2 VA squared plus GHA, and that's equal to this stuff. 1/2 V at C squared plus GHC. Okay? Now, do we have these numbers? Do we have the velocity at A? It's 2, right? 2 meters per second. Do we have G? Yeah, it's like 10 or 9.8. Don't worry about the negative. We have H, it's 50. do we have the velocity at c? No, but we do have the height, so we can figure this all out. I'm going to go ahead and move this over to the left side, so we have 1/2, the velocity at a is 2 squared, plus g is 10. Remember, we don't really care about the negative on the 10. You know, some people usually care about that negative. With energy, we really don't care about it. But we will care about a height and a change of height. But here, the height's just 50. Okay, and I'm going to move that gh over here, so it's going to be minus g, so minus 10. That's where it actually makes sense. The height at c is going to be 25. And this is equal to 1/2 the velocity at c squared. All right, and so if I wanted to solve this for the velocity at c, I would take whatever I get here, I'd multiply it by 2, and then I'd square root it. And so if I did this, I have 2 squared, which is 4, 4 divided by 2, which is 2, plus 50 times 10, so 500, minus 10 times 25, so 250. I'm going to multiply that by 2, and I'm going to square root that. And I get 22.5. So the velocity at c is equal to about 22.5 meters per second. Well, here's the big question. What about the velocity at e? Can we find that? So look at the velocity at e. What kind of energy do we have at e? We've got kinetic energy, right? That's what we said. Is that equal to what we have over here? Sure. So we can write down this equal to this to find the velocity at d. And the big question is it going to be twice as much as that? Okay, that's the big question. So let's write it down. We've got 1/2 the mass, well, the mass canceled out already, so v of a squared plus gha, and that's equal to 1/2 vd squared. Okay. So again, the VA is 2. 2 squared is going to be 4. 4 divided by 2 is just going to be 2, so I'm just going to write down 2. Plus 10, the height at A, which was 50, and that equals 1/2 the velocity at D squared. Well, what is this? So 50 times 10 is going to be 500. 500 plus 2 is going to be 502. We're going to multiply that by 2, so we have 502 times 2, so 1,004. 1,004, and we're going to square root that. So is this twice the amount as 22.5? Well, I don't think so. Let's see. Square root of 1,004 gives me 31.7 meters per second. All right. So we have this change, but just because we changed another 25 meters doesn't mean we get twice as fast. All right. So there you go. Final velocity right there.